Hi everybody, this is Mrs. Ewald signing in, and today we're going to go ahead and talk about entropy. Now you should remember entropy a little bit from biology, because we talk about entropy, especially in honors biology, in the beginning of the year, when we talk about energy, and the whole idea about how the world works. So what I want to do today is go through some examples, and then also get to the big meat of the matter, which is how do we know if a reaction occurs spontaneously or not? So first thing to understand is the definition of what entropy is, and that is the way the world works, and that is that things tend to move from order to disorder. And so that is the way that it naturally occurs. We also show entropy as delta S. Now, you should remember from your last podcast about with Miss Heaton talking about delta H. And so we're going to be taking into consideration delta H as well as delta S and use those two to figure out the spontaneity of a reaction. So first off, to understand a little bit more again about entropy, here we have a few visuals to help you along. So first off here, you have, let's say, gas particles or atoms. And so in this visual here, they're moving about freely and pretty disorganized. Over on the right, you're going to notice that they're tightly packed together into like a crystal structure. So this is more of like a solid. So this is a solid, and this would be a gas. So when it's nicely packed together, nicely in order, we call that organized. So this is order. As they, let's say, heat up, get more energy, more kinetic energy, and start bouncing around, they're going to tend to move in this direction, which is what a gas will do, and try to take the shape of the container. This is now disorder. In order to go in the opposite direction, we would have to cool this down to give it more order, and also energy would have to be put in order to make those bonds again. So energy is required to go in order to get it back to order. Here's another visual. Here you have some bricks which are nicely stacked together. So this is organized. So we'll say this is order. And here it's going to move to disorder. So disorder is more probable than order because, again, it takes little to no energy for that to happen. Another great example of your life is going to be your bedroom. Here you see an office or a bedroom, and what happens is that over time, your room just naturally is going to become disorganized. And I bet you if you're looking at your room right now, it's probably the case. I bet your parents are on you to probably clean it. Now, why don't you want to clean it? It takes energy to go in order to get it organized again. So the easiest thing to do to keep your room organized is to put in little bits of energy at a time in order to keep it that way. So rather than throwing your clothes on the floor or on your chair when you get home, you would put them away right away. And so you're doing little inputs of energy at a time. Otherwise, you end up having complete disorder and having to spend a whole weekend or something cleaning your room up. So we're going to summarize this by saying, when you go from order, and I'm using order, I'm shortening this now. So O meaning order, and then D meaning disorder. So I'm just being lazy here. Entropy, right? Now you can blame everything on entropy. So order to disorder. We would then say that this is increased entropy, so delta S. So we're going to show the increase using the positive sign. Increase. And when you go from disorder back to order, we will say that's negative delta S, so a decrease in entropy. So negative meaning decrease. Okay, so order to disorder is an increase in entropy. Disorder to order is a decrease in entropy. So in order to get back to order, energy is needed to be put in. Little to no order is necessary, little to no energy is necessary to go in this direction. And this is the way naturally the world works. Oops. So, hopefully you understand what entropy is. Again, it's the way things will naturally move from order to disorder. And there are also some variables to think about and consider when trying to figure out if there's an increase or decrease in entropy. So the first one is a change in state. So here looking at this phase change diagram, you know that as you move up, it is considered to be endothermic, so energy is going in. As you move down, it is considered to be exothermic. And so when you go, let's say, from a solid and form into a liquid, so solid to a liquid, okay, so we're moving up, what would you consider that to be as far as order? And so let's think if this is increased or decreased entropy. So if I'm going from a solid, which is nicely organized, into a liquid, which is now going to be separated slightly, this would then say is order to disorder. And so we're going to call this positive delta S. Again, increase in entropy. If you go, let's say, from a gas to a liquid, so now what we're trying to do is bring order, so we're going from disorder to order. We would say that this is negative delta S, or a decrease in entropy. And so a change in state we could look at and think about what are the arrangement of those atoms and then figure out the entropy from there. Temperature also is going to play a role because if you're increasing the temperature, you're more than likely going to be creating a gas or heating it up, causing more disorder. So you know that when you're in a dance, as soon as it starts getting hotter in there and you're running out of room, things tend to become quite unorganized, right? Also, too, the size of the container is going to definitely influence it. If you have a smaller container, you could tend to try to have some more order versus having a larger container, and now things are all over the place. So if you think about your classroom, the larger the classroom, the harder it is to keep order. And then also the number of particles. The more people you add, the more disorganization you might have. So those are some conditions to think about when thinking about if you have an increase or decrease in entropy. So always think about those scenarios. So now let's talk about spontaneity. Now, we do know from biology as well that anytime you have a reaction, you're always going to have some type of activation energy, or some energy is going to have to be put in. But we could also look at delta H and delta S. So we're going to be looking at the change in heat energy as well as the change in entropy. So the enthalpy and entropy. So if delta H is negative, right? So you have a negative delta H. What does it mean? It means that it is exothermic. So energy, overall, the net amount of energy is given off in the reaction. That is a favorable condition, meaning it's very likely to happen, and it requires little to no energy in. If you have a positive delta H, so that is endothermic, that is considered unfavorable because, again, energy is going to be required. So what this means then is it's less favorable if you have an endothermic reaction for it to be considered spontaneous. And so hopefully you know what it means to be spontaneous. So it means to be able to have the reaction with very little catalyst or anything like that to get it going. So if you think about a spontaneous person, you know, really just all they really need is just one trigger and they'll go, right? When you talk about entropy then, what makes it favorable or unfavorable? If you have a positive entropy, so an increase in entropy going from order to disorder, that is favorable. Okay? Because that is the way the world naturally is going to work. If you have a negative entropy, then we would consider that unfavorable because, again, energy is going to need to be put in, so it's less likely for it to be a spontaneous reaction. So let's go through some examples then to figure out spontaneity. So we're going to be looking at here both entropy and enthalpy, and I'm going to show the symbols as well. So, if you have negative entropy, so what does this mean? It means that we're going from disorder to order, and this is going to be considered unfavorable because energy is going to need to be put in. You have a decrease in entropy, not likely for it to be spontaneous when you look at the entropy. When you look at delta H, if it is negative, we know that it's exothermic, and that would be favorable. Okay, so now looking at these two conditions, you have to consider delta S and delta H to figure out whether or not it will be spontaneous. So knowing that the entropy is unfavorable and my enthalpy is favorable, what it's really going to depend on then is the temperature. And so based on the temperature, we will know exactly then how likely it is for it to be spontaneous. So we cannot say yes or no. We will say it depends on the temperature, whether or not it will be spontaneous. Now if you have a negative delta S again, so disorder to order, again that's going to be unfavorable. But now we have positive enthalpy, so that means it's endothermic, which is also unfavorable. It is very likely, because of these two conditions, they're both being unfavorable, that the reaction is not going to be spontaneous. It's going to need some kind of catalyst or trigger or something to get it really going. Okay? If you have a positive delta S, that means you're going from order to disorder. That is favorable. And if your enthalpy is exothermic, which is also favorable, now we know for sure we're going to have a spontaneous reaction. They're both favorable conditions. It's exothermic. It's going in the way the world works. It's a beautiful thing. It's going to move. If you have something positive again, order to disorder, that would be favorable. And if you have something that's endothermic, that would be unfavorable. Just like what we saw in the first example, it's going to depend on the temperature. Okay? So what you're going to need to be able to do in class then is be able to figure out, based on a scenario, whether or not you have an increase or decrease in entropy, and then also be able to determine the spontaneity of the reaction. So I would make sure you could go through this table, understand that well enough to be able to figure out spontaneity, as well as going back to this table, because it's very, very easy to kind of get a good way of figuring that out. For example, if you have two negatives, it's going to depend on temperature. If you have two positives, again, it's going to depend on temperature. So you could kind of figure out that way, also spontaneity. Okay? So this is Mrs. Ewald signing out, saying yay for entropy. And yeah, that's it. So peace out.